Hello friends. So today we are going to solve 4 questions, and these 4 questions are from the fields of a moving charge based on the topic. And so in the first question, it states that in a colliding beam, storage a ring, an antiproton going east passes a proton going west, the distance of the closest approach being 10 raised to the power minus 10 meters. The kinetic energy of each particle in the lab frame is 93 giga electron volt, corresponding to gamma is equal to 100. In the rest frame of the proton, what is the maximum intensity of the electric field at the proton due to the charge on the antiproton? For about how long approximately does the field exceed half its maximum intensity? So in this case, we have two charges, one is proton and other one is antiproton. And the basic calculation or which we are going to solve is for the rest frame of the proton. So everything should be, the frame is with respect to our rest frame of the proton. And the proton and antiproton are moving in opposite direction in the lab frame. So first of all, we are going to find out what will be the relative Lorentz factor in proton rest frame. Okay. Because the gamma that is given, it is given with respect to our lab frame. Okay. So, but we have to calculate everything with respect to the proton frame. So we are going to find out relative Lorentz factor in proton rest frame. And we are going to call this as gamma relative. So we can say our gamma relative will be equal to our gamma square 1 plus beta square. And in a highly relativistic motion, we can assume that beta is approximately equal to 1. So you can say our beta is approximately equal to 1 for our highly relativistic motion. Highly relativistic motion. Therefore, we can write that our gamma relative will be approximately equal to 2 times gamma square, and gamma is given to us as 100, so this becomes a 2 times 100 square, and this can be written as 2 into 10 raised to the power 4. And now we are going to find out the electric field of this relativist motion, or we can say moving charge. So you can say our electric field of a relativistic moving charge. And so in case of this relativistic motion for a moving charge, our transverse electric field is enhanced. Okay? It means the perpendicular direction of the magnetic field will be our enhanced version of the original electric field. And the formula for that, we can write that the value of the electric field, which is our transverse, is going to have a maximum value, and this maximum value is given by our Q times gamma, and this is 4 pi epsilon naught and beta square. Here not beta but b square. Here b is nothing but our distance of closest approach, which is already given to us. So we simply substitute the values. 1 upon 4 pi, we can write this as our 9 into 10 to the power 9. Charge we know is a 1.6 into 10 to the power minus 19, and this gamma is our 2 into 10 to the power 4. Okay, we just calculate this is gamma relative. Okay, let me write it here. This is gamma relative, and we are left with b square, that is distance of closest approach, which is 10 to the power minus 10 and whole square. So we get this value will be approximately equal to 2.9 into 10 to the power 15 volts per meter. Okay. And secondly, we are supposed to find out that the duration of this pulse, and that is based on the standard formula. We can write that duration of the field pulse, that is given as our delta of t, will be approximately equal to b upon gamma times c. Okay, here gamma is nothing but our gamma relative, because the frame of reference is our proton that is at rest. So we found out this is gamma relative times c, and c is the speed of light, and b is our distance of closest approach, which is given to us. So this becomes 10 to the power minus 10, 2 into 10 to the power minus 4, and c is our 3 into 10 to the power 8, and this approximately comes as our 1.7 into 10 to the power minus 23 seconds. So this delta of t, delta of t, that is a small amount of time, it is nothing but the field exceeds its half of its maximum value for this duration of time. That is definition of this delta of t, which is also called as a duration of the field pulse. Okay. Next question. It states that a capacitor consists of two parallel rectangular plates with a vertical separation of 2 cm. The east-west dimension of the plates is 20 cm and north-south dimension is 10 cm. The capacitor has been charged by connecting it temporarily to a battery of 300 volt. What is the electric field strength between the plates? How much excess electrons are on the negative plate? Now give the following quantities as they would be measured in the frame of reference that is moving eastward relative to the laboratory in which the plates are at rest, with a speed 0.6 times c. The 3 dimensions of the capacitor, the number of excess electrons on the negative plate, the electric field strength between the plates answer the same question from the frame of reference that is moving upward with a speed of 0.6 times c. So basically this entire question is in three parts. First we are going to solve it for our normal, that is our everything is you can say the plates are at rest, or we can say in the laboratory frame. Then it is said that the plate is moving eastward, that is second part, and then it states that it is moving upward, so that is our third part. So we are going to start with our when the plates are at rest, or we can say in the laboratory frame. So you can see in the lab frame, or you can write that plates are at rest, which is our normal condition. Plates are at rest. And so first of all, because we need to find out the electric field, and electric field we know is our potential divided by the distance. Okay, and so let us write our standard formula for electric field. Our electric field, that is our E, is equal to our potential divided by the distance between the plates. Potential, that is our 300, and the distance between the plates is given to us as 2 centimeters. Okay, so this will be 0.02. So we get the electric field will be equal to 1.5 into 10 to the power 4 volts per meter. And obviously the direction will be from the positive plate to the negative plate. So here we can just write the direction, and direction we know that it will be from positive plate towards the negative plate, or we can say it will be in vertical direction. And then we are supposed to find out we got the electric field, and we are supposed to find out the excess of electrons. And for that, first of all, we are going to find out the charge, and from their charge we can find out what will be the number of electrons present. Okay. So for charge, we are first of all going to find out the capacitance of the parallel plates, and then we are going to find out the charge. So you can see our capacitance of parallel plate capacitor, that is where C is our epsilon naught A upon D, and epsilon naught is our 8.85 into 10 to the power minus 12, and A is our area, and area will be product of their dimension, which is our 0.2 multiplied by 0.1, and D is the distance, which is our 0.2. Therefore we get that our capacitance C will be equal to, this will be our 8.85 into 10 to the power minus 12 farads. And from here we can find out our charge, that is our Q, is equal to C times V, and C is our 8.85 10 to the power minus 12, and voltage is our 300. Therefore we get that the value of the charge Q is our 2.66 into 10 to the power minus 9 coulombs, and we are supposed to find out the number of electrons. Okay, so we can say the number of electrons n will be equal to total charge and charge on one electron. So this comes as 2.66 into 10 to the power minus 9 and 1.6 into 10 to the power minus 19. So number of electrons, that is value of n, will be approximately 1.7 into 10 to the power 10 electrons. So we are able to find out the electric field, and we also find out the number of excess electrons or number of electrons that will be associated with our this field, or we can say the parallel plate capacitor. Now we come to our part B, in which we are going to discuss our moving frame. And in the first part of it is B part, it is given that the moving frame is moving east at 0.6 times c. So we can say frame moving east at 0.6 times c. Therefore, from here we can write that our beta is equal to 0.6. And therefore we can write that our gamma is equal to 1 upon 1 minus beta square. That is the standard formula, which gives us 1 upon 1 minus 0.36 times square root, and it's approximately equal to 1.25. And now we can find out, because it is going to move towards east, or we can say motion is our east-west. Therefore, the length specifically with respect to the east-west is going to contract. Okay, and this contraction will be based on the original length and divided by our this factor. Okay, Lorentz force. Because of the Lorentz force, the east-west length is going to contract. Okay, so dimension is going to change. Therefore, we can write that our motion is east to west. Therefore, we can say that only east-west length contracts, and we can write that the length, suppose that is L prime, and that is between east and west, will be equal to the original length, that is our 0.20, and divided by this factor, that is gamma, that is our 1.25, and this will be coming as 0.16 meters. Okay. So only the length about the east-west contracts, changes rather, and the north-south remain unchanged. Okay, you can say our north-south is unchanged, and this length will be same as the previous one, original one, that is about 0.10 meters. And the separation between the plates is also going to remain unchanged. Therefore, we can say the separation also is our unchanged, and that is also our 0.02 meters. And we know that our electric field, or we can say electric charge, is independent of this Lorentz factor, that's our gamma. Therefore, the number of excess electron will also remain unchanged. So number of excess electron before and after this motion will be same. Okay, that is not going to change. So we can write that our electric charge is Lorentz invariant. Therefore, you can say that number of electrons, let us suppose this n prime, will be equal to over n, that is 1.7 into 10 is power 10. So number of electrons are going to remain same. And the value of electric field, which is perpendicular to motion, is going to change by a factor of gamma, okay, because the changes. Therefore, we can write that our field, like we said, is vertical. Okay, we have already, it is from positive to negative plates, and its direction is our vertical, which we have already discussed. So we know that our field is vertical, or we can write this will be perpendicular to motion, and therefore its new component, the perpendicular component prime, will be equal to the Lorentz factor gamma and its original electric field E, and therefore we get this as our 1.25 times 1.5 into 10 is power 4, and this comes approximately as 1.9 into 10 is power 4 volts per meter. And next, in the part C, it is asked that the frame is moving upward at a speed of 0.6 times c. So now we are given that our frame is moving upward at 0.6 times c. Now our electric field is also vertical, that is in upward direction, and the motion is also upward direction. So therefore we can say that the motion is parallel to the electric field. So we can say that our motion is parallel to our electric field, and therefore only the vertical dimension, or we can say specifically the separation, is going to change or contract, okay, and other dimension, that is length as well as breadth, is not going to change. So we can say only vertical separation contracts. And suppose that is given as d prime, and this d prime will be equal to our gamma, it will be our original dimension, that is 0.02, original separation divided by the gamma, that is our 1.25, and this will be our 0.016 meters, and the other dimensions, that is length as well as breadth, is going to remain unchanged. So it will be 0.02, 0.20 as well as our 0.10 meters. So these two dimension, length and breadth, is not going to change. And like we said, that our electric charge is independent of this Lorentz factor, which is our this gamma, which we calculate here, and therefore the number of electrons in this moving frame upward is also going to remain same. Okay, it's not going to change. Therefore we can write that number of electrons, let us call this as n double prime, will be equal to the original one, that is of n, and that is 1.7 into 10 to the power 10. And the electric field, that is of a parallel electric field, it will be the independent of our, because the motion as well as the electric field are parallel to each other. Therefore we can say that of electric field is our E parallel prime. This will be equal to our electric field parallel, which is our original electric field. So field is not going to change. This will be our same 1.5 into 10 to the power 4 volts per meter. So from here we can see that how the motion, only some specific values or specific parameters are bound to change according to the direction of the motion. Not all the factors are changing. Next question. It states that a beam of 9.5 mega electron with gamma is approximately 20, amounting as a current to 0.05 microampere, is traveling through a vacuum. The transverse dimension of the beam is less than 1 millimeter and there are no positive charge in or near it. So based on this, we have two parts. In the lab frame, what is the average distance between the electron and the next one ahead of it, measured parallel to the beam? What approximately is the average electric field strength 1 centimeter away from the beam? Answer the same question for the electron rest frame. Okay, so frame in the part B, the frame has been changed. So first of all, we are going to find out the value of the beta, that is our speed factor, how it is going to change. And so we can say that is our beta, its formula is 1 upon 1 and gamma square and its square root. So gamma is about approximately given as 20, so this comes as 1 upon 400 square root. So approximately this will be equal to our 0.999. Therefore we can write that our velocity, our normal formula is velocity is equal to beta times c. Okay, so this beta, we can say this is approximately nothing but value of our c, which is 3 into 10 to the power 8 meters per second. And now we are going to discuss the question with respect to lab frame, and then we come to our electron rest frame. So in the lab frame, we are supposed to find out the average distance between the electrons. And so the average spacing is given as d is equal to 1 upon the number of electrons per meter. Okay, for that, first of all, we require to find out our current relation, density, and then we come to our number of electrons per meter. Okay. So let us start from our that. Let me write the average spacing, which is our final requirement. So you can say our average spacing, it is d is equal to 1 upon NL, and here this NL, it is our number of electrons per meter, number of electrons per meter, and it is given as our lambda upon E, and this lambda is charge per unit length. charge per unit length, and this is nothing but our current divided by the velocity v. Okay. And so current is given to us. So first of all we are going to find out our lambda. So we can say our lambda is, our current is given as our 5 microampere, that is 5 into 10 to the power, sorry, not 5 microampere but 0.05 microampere. So this comes as 5 into 10 to the power 8, and velocity is 10 to the power over 8. So we get the charge per unit length is our 1.67 into 10 to the power minus 16. And from here we can easily find out our value of this number of electrons per meter, and this comes as our 1.67 into 10 to the power minus 16, and charge is our 1.6 into 10 to the power minus 19. So this approximately is equal to 1 into 10 to the power 3, and then we can easily find out our value of d. So we can d is equal to 1 upon our 1 into 10 to the power 3, so approximately equal to 10 to the power minus 3, or we can say this is 1 millimeter. And then we have to find out the value of electric field 1 centimeter from the beam. You can say that our electric field one centimeter from the beam, and if we treat the beam as our infinite line charge, so we can easily use that particular formula. So we can say for beam as infinite line charge, therefore we can write the value of electric field will be equal to our lambda upon 2 pi epsilon times r. And we already know our lambda as well as r, and 2 pi epsilon is our standard. Therefore we can write that value of electric field is equal to our 1 upon 2 pi, this will be equal to our 1.8 into 10 to the power 10, lambda is our 1.67 into 10 to the power minus 16, and the distance is over 1 centimeter, which is about 0.01. So we get the value of electric field in the lab frame. So let me write this as a lab will be equal to approximately 3 into 10 to the power minus 4 volt per meter. And now we come to our the rest frame. So we can say our electron rest frame, and obviously we know when the frame is going to change from the motion to the rest or rest to the motion, the Lorentz factor, that is our gamma, comes into the picture, okay, which we have already derived, that is our gamma. Therefore we can say that first is our electron spacing, and because the length runs parallel to the motion, so that will be result in our, we can say, from the rest frame. So we can say our electron spacing, and we can say our length parallel to the motion, expand while when going to the rest frame. well, going to rest frame. Therefore, we can write that our d prime will be equal to our Lorentz vector gamma times the original dimension, that is our d. Because there is an expansion, so obviously it will be a multiple factor. So this comes as 20 into 10 to the power minus 3, which can be approximately written as about 2 centimeters. And our electric field because in the lab frame, or we can say the field in the lab frame is perpendicular to the motion. Okay. So we can say the field in the lab frame is perpendicular to the motion. Therefore, we can write that our perpendicular magnetic field E prime perpendicular will be equal to the original perpendicular magnetic field divided by the factor, that is our gamma. And this comes as 2 into, sorry, not 2 but 3 into 10 to the power minus 4 divided by 20. So this comes approximately as our 1.5 into 10 to the power minus 5 volts per meter. So we can see how the motion changes or dimension changes or electric field changes when there is a shift in the frame. Okay, and that is our expansion as well as our contraction. Next question. We are given that a stationary proton is located at z on the z-axis at z equal to a. A negative muon is moving with a speed of 0.8 c along x-axis. Consider the total electric field of these two particles in this frame at the time when the muon passes through the origin. What are the values at that instant of Ex electric field in x as well as electric field in z at the point a, 0, 0 on the x-axis. So basically we have to find out the value of electric field and when it is at the point that is our a, 0, 0. And we are given that a proton is at rest, only the muon is moving. So we are going to evaluate the field at the instant when the muon is at the origin. So let's find out what with the field of the proton. And the proton is at rest. So if the body is at rest, we can simply use the basic formula to find out its value of the electric field. So you can say field of the proton. And our proton is nothing but a stationary at the our 0, 0, 8. Okay. Yeah, proton is located at z-axis. So this is a stationary at 0, 0, a. And the field point is our a, 0, 0. So we have to find out the distance between the two. So we are given that our proton is at 0, 0, a and our field point is our a, 0, 0. Therefore, the distance, we can say that value of r will be equal to our with this will be our A0 comma A, okay. Or we can write this as our A0 comma minus of A, and if we find out its magnitude, that is R will be equal to our A square plus A square and its square root, which will be coming as A square root of 2. Therefore, the value of electric field will be equal to 1 upon 4 pi epsilon naught, and this is our E, that is charge, and our R cube and our R vector. And so we get this of E will be equal to 1 upon 4 pi epsilon naught E upon 2 square root of 2 over A cube, and our R vector is A comma 0 comma minus of A. And from here we can easily write its components. Its x component will be equal to 1 upon 4 pi epsilon naught E, and this comes as 2 square root of 2 A square, and z component is equal to minus 1 upon 4 pi epsilon naught E upon 2 square root of 2 and A square. Okay. Obviously our y component will be equal to 0 because its coordinate is our 0. Now we come to the field of a moving when the muon is moving. You can say the field of the moving charge, and here charge is nothing but our muon. And charge on the muon is nothing but our negative of the charge of our electron. Okay. And first of all, we are going to find out because now the charge is moving, so one factor, that is our Lorentz factor, comes into the picture. So we can say our Lorentz factor gamma will be equal to 1 upon 1 minus beta square, and beta is our 0.8, so this comes as 1 minus 0.64 square root, and that will be equal to our 1.667. And we have to find out when the muon is at the origin and the field point is our A comma 0 comma 0. So we have to remember that our muon is at our origin and the field point is our A comma 0 comma 0. So therefore we have to find out the value of electric field, and now we have to find out, rather we can say we are going to use the formula for electric field when the charge is in motion. Okay. So we can say for a uniformly moving charge, the electric field is equal to 1 upon 4 pi epsilon naught q upon r square, and this is 1 minus beta square and 1 minus beta square sine square theta and whole raised to power 3 by 2. Okay, so this is our formula for electric field because of a moving charge, and the muon is at the origin and the field point is our A comma 0 comma 0, which is nothing but our x axis. Okay, so we can say the point lies along the direction of the motion. So theta will be equal to 0. So we can say that our point lies along direction of motion. Therefore, our theta is equal to 0, or we can say our sine of theta will be also equal to 0. Therefore, electric field, because of the muon, we can simplify this as 1 upon 4 pi epsilon naught q, and the distance is nothing but our a, so this comes as a square, that value of r, and it is 1 minus beta square. So now we can easily substitute the values. We get this is equal to our okay, so it will be 1 upon 4 pi epsilon naught. Charge is our charge negative of our electron, and a square, and this is beta is our 0.8, so that will be 0.64, so it will be coming as 0.36. And our electric field is purely in x direction, so we can say that E of mu is nothing but E of mu x, which will be equal to our minus 1 upon 4 pi epsilon naught and 0.36 times E upon a square. And electric field of the muon in z direction will be equal to 0. And so now we can easily find out what will be the our total electric field. Okay. And for that, because we found that electric field because of the muon in x direction, and electric field because of the our proton in x direction as well as z. So you can say our total electric field So first of all, we are going to solve for our E of x, which will be equal to our 1 upon 4 pi epsilon naught E square, and this comes as 1 upon 2 square root of 2 minus 0.36, and this will be our E of x will be 1 upon 4 pi epsilon naught E a square, and we can just sort it out. This will be coming as minus 0.006. And in z-axis, only the electric field because of the proton contributes. The electric field because of the muon is equal to 0. Therefore, we can say that our E of z is equal to electric field because of proton in z direction, which is minus 1 upon 4 pi epsilon naught, and this comes as our 0.354 E divided by a square. So this is the value of our electric field. Therefore, we can clearly see that whenever the charges are in motion, it changes how the value of electric field as well as our only electric field changes because the number of electrons are not going to change. So this completes all the questions for today. Thank you.